Okay, so here we're looking at the properties of trapezoids. Now, there's four big properties that we want to um, take a look at or investigate. And I want to get started with just a generic, basic trapezoid. And before we even do that, what is the definition of a trapezoid? Excuse me. A trapezoid is a quadrilateral with at least one pair of parallel sides. Okay, so let's draw a figure that has one pair of parallel sides. Now, again, I just use this block because it's nice. I know that these two sides are going to be parallel. So I'm going to draw just a generic, basic um, trapezoid. I don't like that, but oh well, we're going to deal with it. And here we have this side length, and over here, sorry for turning it on you, we have this side length. Okay, so now here, the top and the bottom are called the bases, right? So here, this is one base, and here, this is another base, right? So we have the two bases. The parallel sides would be considered the bases. The non-parallel sides of a, I would call it irregular or scalene trapezoid, these are just considered the sides. So we have bases and sides, right? And we could label this thing, we could label it A, B, C, D. Okay, so because of the properties that of a trapezoid, right? These are parallel sides. If I were to extend this line out and that line out, the bases, if I were to extend those lines out, and then this side length would be considered a transversal. So that means that this angle right here, and get a different color other than green, we'll call blue. Okay, this angle right here, these two angles. So these two angles would be considered same side interior. All right, so the first property. So the first big property is that the same side interior angles, same side interior angles are supplementary. All right, so they're not on the same base. Remind you that they're not on the same base. So opposite bases, but on the same side. Okay, those are going to be supplementary. This one plus this one is going to add up to 180, meaning they add up to 180. If you haven't heard me or us say supplementary at least 500 times, then something's wrong. Here we have the red angle, and see, we did green. Ooh, we haven't done orange. The red and the orange, these two angles. Ooh. Right, so these two angles would be considered supplementary. Right, so they add up to 180 degrees. So that's the first property that we're going to take a look at. All trapezoids, regardless of whether it's an isosceles or right trapezoid, it doesn't matter what type of trapezoid it is. Right, the same side, meaning not the same bases, but the same side of the transversal. These two are going to be supplementary, and these two are going to be supplementary. Okay, that's cool. Now, here's something that I find to be completely amazing. The other thing we can take a look at is what's called a mid-segment. Now, we discussed mid-segments last time, but I'm going to measure this out. So I'll measure this line here. In millimeters, we're looking at 67, 68, 65, 67. All right, so half of 66 is 33. So 33 and a half, somewhere around there. So 33, 1, 2, 3 and a half, somewhere right about there's the mid segment or midpoint of that A line of AD. And then we're going to find the midpoint of this one, BC, the midpoint here. So we're at 70, 71, 72, 71, 72, 71, 72, 70 half. So let's go 35 and a half-ish, somewhere right about there is going to be the midpoint of this one. All right. So if I draw a from midpoint to midpoint right here, midpoint to midpoint, this line right here is called a mid-segment. This line segment is in the middle of AD and BC, so it's called a mid-segment. All right, so let's take a look. There's some pretty neat properties about this mid-segment. All right, so the second property that we're going to have has to do with mid-segments. All right, so let's take a look. The first thing I'm going to do, I'm going to measure the distance from A to B. So the distance from A to B, oh, it's right at, you know what? It's between 49 and 50, but closer to 50. So we're going to call this 50 millimeters there. And then the distance on the bottom one, no way. Let's call it 91. Here we have 91 millimeters. Okay. So if I know the distance of the first base and the distance of the second base, what do you think is the distance of the mid-segment? How would we go about finding it? Now, the mid-segment is found by the midpoint of A to D. Let's call it E. And the midpoint of B to C, let's call it F. All right. What do you think the distance is of that mid-segment? We measured the AB to be 50, DC to be 91. Pause right now, try and figure out what it is, and then come back and tell me if we got it correct. Okay, now that we're back, let's take a look. I bet, and this is just me throwing wild guesses out. I bet that it's halfway, because EF, this line is halfway between the two, so the distance here must be halfway between 50 and 91, right? And half the distance between 50 and 91, half the distance. That would be an average, right? So let's take the average. So how do we take the average? We take the two, add them together, and divide by the number that we have. So 1, 2, there's two of them. So we'd say 50 plus 91 divided by 2. Well, that gives us a total of, oh goodness, 141 divided by 2. So 141 divided by 2. And when I plug that in my calculator, I get 70.5. Oh, 70.5. Now I'm going to say that the distance from E to F is 70.5. Hey, bud. Sorry, Louis wanted to make an appearance. All right, here we go. Let's measure it out from here to there. Whoa. I don't know if you can read this really well. I'm going to try and let it zoom and focus, but that is about as spot on as it could possibly be. Right at 70.5 millimeters. 70.5 millimeters. All right, Lou, hey, go get your mom. Go to the living room. Go get your mama, okay? No, it's not time to play. Daddy's doing work. I know. It's crazy. Okay. So the second thing we could say, the mid-segment now, as we've seen, yeah, that's right. The mid-segment is the average of the bases. Ooh, all right, so the property here, mid-segment is the average of the bases. So the length of the mid-segment is the average of the length of the bases. And here's how we're going to write that. So let's, for mid-segment, let's just use M. So M would be, so average the bases. So base 1 plus base 2, right? What we did, base 1 plus base 2 and divided by 2, because there's 2 of them. So we're going to divide that by 2. And now we have a formula, right? The mid-segment is the average of the bases. The mid-segment equals base 1 plus base 2 divided by 2. All right. So that, I think, is really, really cool. If you wanted to manipulate this a little bit, you could multiply both sides by 2 real quick. And another way of looking at this, so the same exact formula, we could write it as 2 times the mid-segment is equal to base 1 plus base 2. So that might be helpful if you don't like this fraction, you could look at it like this. But I'm going to use this version right here. This, I think, is going to be the most helpful. All right. So we have 2 more properties to take a look at. there's a different type. There's a unique type of trapezoid, and this trapezoid is called an isosceles trapezoid. All right, what do you think it means to be an isosceles trapezoid? Well, an isosceles trapezoid means that the two side lengths are equal. Now, I can make an isosceles trapezoid. Hopefully I can make it. And then let's go here to here. Okay, so an isosceles trapezoid means that I have a pair, or yeah, one set of parallel sides, right? Here's my parallel sides, and these side lengths are equal. And I could show you that by measuring here. We're at what, 25, 27 millimeters there. Here we're 27 millimeters there. Yeah. So this side length and this side length are equal, and that's how we could denote that. Okay. First thing we're going to take a look at. So our third property of trapezoids has to do with isosceles trapezoids. So if the two side lengths are equal, then that means that the base angles are going to be equal. And we already know that the same side interior, these two are going to be supplementary, but our base angles are going to be congruent. That is a really special property. So here we could say that the base angles are congruent. Now, that also lets us know that opposite or diagonal angles would also be supplementary. Ooh, that's kind of an interesting way of thinking. So I'm going to write it like this: A, B, C, D. So trapezoid A, B, C, D. We could say that angle A plus angle C are going to equal 180 degrees. These are going to be supplementary, as well as angle B and D are going to be supplementary. So if they're across from each other like that, they're also going to be supplementary. So the real property states that the base angles are congruent, but there's a lot of really cool. Once you know that the base angles are congruent, then what you could say is there's several other properties that come along with that. In other words, the angles across from each other also happen to be supplementary, meaning they add up to 180. So angle A and angle C would add up to exactly 180 degrees. That, I think, is pretty fascinating. All right, there's one more, the last property that we have, the final property, and we could do this again with another isosceles trapezoid. So let's do this again. We're going to go here to here, and we'll try and make it perfect. It wasn't exactly perfect last time, but see if I can do it this time. And here to here. Okay, another isosceles trapezoid. One thing that's pretty neat about an isosceles trapezoid, because of the way that it's created, we know that these two side lengths are the same. And let's call this one, instead of ABCD, let's call this guy EFGH. So property number 4, the fourth property that we're going to take a look at. If I were to create a diagonal, so the diagonal here that runs from F to G, that wasn't perfect, but oh well. Or I'm sorry, E to G, excuse me, and then from F all the way to H. That one's a little better. What do you think you could say about these diagonals? Right, the distance from F to H and the distance from E to G. What do you think? Well, let's measure them out and see. So the first one, the first diagonal from E to G, about 42, roughly 42, between 42 and 43. Oh, let's see. The diagonal here, oh wow, that was almost spot on, even though it's ugly. Between 42 and 43, right? So what we could say is the diagonals of an isosceles trapezoid are congruent. Congruent. Yay. Woo! Another way of writing that out would be, for this trapezoid, we could say that the distance, or the line segment from E to G is congruent to the line segment from F to H. And in the next video, we're going to do a couple of practice problems, some examples.